Welcome back to the Science Corner, everyone. This is our spot for, getting into the really fascinating science questions for all you intellectually curious folks out there.
Glad to be here. It's always fun to explore these big ideas.
And today, we're tackling something pretty mind-bending, even for theoretical physics. The idea that gravity, well, that it might not be fundamental.
Exactly. The theory we're discussing suggests gravity could actually emerge from something else, something related to entropy.
Entropy, right. The measure of disorder or maybe information in a system. So our mission today is to sort of unpack this. How can gravity, the force holding galaxies together, emerge from information?
It sounds counterintuitive, I know.
Yeah.
But the thinking draws on some really cutting-edge research, trying to weave together gravity, quantum mechanics, statistical mechanics, and information theory.
A real mashup of fields. Okay, so where do we even begin? What were the first hits that gravity and entropy might be linked?
Well, the story often starts with black holes. It was quite a shock back then, the realization that black holes actually have entropy.
Right, Beaconstein and Hawking's work, that black holes aren't just simple voids.
Precisely. They have a temperature, they possess entropy, and Stephen Hawking showed they even radiate. Hawking radiation.
Which implies they aren't truly black.
But not eternally, no. And this was huge because it forged this unexpected link between gravity, which describes the black hole's structure, and thermodynamics, the physics of heat and, well, disorder or entropy.
Okay, so black holes open the door. But that's a pretty extreme corner of the universe. How do we get from there to suggesting all gravity might be entropic?
That's a more recent development. Researchers started looking deeper into connections between information theory and gravity, especially concepts like entanglement entropy.
Entanglement entropy. That's about how connected quantum particles are, right? Even across distances.
Yes, exactly. And ideas like the holographic principle gain traction.
Ah, the hologram idea, that all the information in a volume of space might actually be encoded on its boundary, like a 2D surface describing 3D space.
Sort of, yeah. That's the gist. The holographic principle, along with studies of entanglement in quantum field theory, provided more, let's say, mathematical threads connecting gravity and quantum information.
It makes my head spin a little. It's like the fabric of space-time itself is somehow built from bits of quantum information.
That's a good way to think about it. It paints a picture where space-time isn't just a passive stage, but maybe an emergent property of underlying quantum information processing.
Okay, so people started thinking maybe we can build a theory of gravity from these information concepts, derive Einstein's equations or something like them.
That became the goal. To formulate gravity using the tools of information theory and statistical mechanics, aiming for, perhaps, modified versions of Einstein's equations.
Modified equations. Why modified?
Well, the hope is that such a theory might naturally explain things standard gravity struggles with, like maybe dark energy, or even offer a path towards unifying gravity with quantum mechanics, the quantum gravity problem.
The Holy Grail. Right. Okay, so that's the motivation. Now, let's get into the specifics of the research we're looking at today, this idea of an entropic action. What's the key move here?
The really novel idea, I think, is to treat the space-time metric itself, the thing that defines distances and curvature, as a kind of quantum operator at each point.
Whoa. Okay, so not just a smooth geometrical field, but something with quantum properties.
Exactly. At the most fundamental level, space-time geometry itself is proposed to be quantum mechanical. It's described in this framework by something akin to a density matrix, if you're familiar with quantum mechanics terminology.
A density matrix describing space-time geometry. That is radical.
It is. And within this picture, we talk about two metrics. First, there's the familiar space-time metric, let's call it G. That's Einstein's curve geometry.
Okay, standard stuff.
But then there's another metric, let's call it G, which is induced by the matter fields present in that space-time. It describes how the quantum nature of matter wants to curve space-time.
So G is the actual curvature, and G is the curvature suggested by the matter's quantum state.
That's a good way to put it. And the core proposal is that the fundamental action, the thing that dictates the laws of physics, is the quantum relative entropy between these two descriptions, between G and G.
Quantum relative entropy, measuring the difference or the distinguishability between these two quantum descriptions of geometry.
Precisely. It's a concept borrowed from quantum information theory, related to things like the Iraqi relative entropy, which is used to compare states in advanced quantum theories. It quantifies how much surprise there is in finding the geometry to be G when the matter suggests it should be G.
So gravity emerges from minimizing this quantum information difference. Nature tries to make the actual geometry match the geometry suggested by matter in an information theoretic sense.
That's the underlying principle, yes.
Now, the research mentions describing matter using topological matter fields. Sounds complex. Why this specific approach?
Ah, yes. This is a particular mathematical formalism for describing bosons, the force-carrying particles. Instead of just simple scalar fields, it uses a combination of what are called zero forms, one forms, and two forms.
Different kinds of mathematical fields.
Right. Think of scalars, vectors, and rank 2 tensors, basically.
Hmm.
This Dirac-Hehler type description turns out to be quite powerful, and it's actually gaining traction in other areas too, like network theory and certain types of quantum field theories on lattices.
Okay, so it's a sophisticated way to describe the matter content. And how does this specific description influence that matter-induced metric, G?
The metric G induced by these topological fields can be expressed quite elegantly using something called the Hodge-Rack operator. It's a mathematical tool that naturally incorporates the geometry and topology of space-time and how these different forms interact within it.
Got it. So you have this entropic action based on the difference between G and G, with G defined via these topological fields and the Hodge-Rack operator. How do you get from that action to, say, Einstein's equations?
The derivation is a bit technical, but it involves introducing an auxiliary field, often called the G field, or G tilde in the papers. Think of it like a mathematical helper variable.
A calculation trick.
And initially, yes, perhaps. But by using this G field, you can manipulate the entropic action. And remarkably, when you vary the action to find the equations of motion, the part describing gravity looks very much like the standard Einstein-Hilbert action from general relativity.
It reproduces general relativity.
Almost.
Okay.
It's what we call a dressed Einstein-Hilbert action. It's slightly modified, and interestingly, it comes with an emergent cosmological constant, a term related to the expansion of the universe.
Wow, okay. A cosmological constant just pops out naturally.
It seems to, yes. And this emergent cosmological constant depends only on this auxiliary G field. And crucially, the resulting equations of motion are still second-order differential equations, which is generally a desirable feature for gravity theories.
That avoids some theoretical problems, right? Okay, that's pretty abstract. The research includes a simpler example, a warm-up with just scalar fields. How does that help illustrate things?
It's a nice way to see the core mechanism without all the complexity of the topological fields. So imagine a universe with only a simple, complex scalar field, like the Higgs field, but simpler.
Okay.
In this case, the matter-induced metric G is just the background metric G, plus a term proportional to the gradient of the scalar field, basically, how the field changes in space and time.
So the field's variation directly influences this second metric.
Exactly. And if you then calculate the entropic action, the relative entropy between G and the simpler G, and derive the equations for the scalar field, you find something familiar.
What emerges?
In the limit where the coupling is weak, you recover the standard massless Klein-Gordon equation for the scalar field.
The Klein-Gordon equation. That's fundamental in quantum field theory for describing particles like scalars.
It is. So it shows that even this very different starting point, based on entropy, can connect back to established physics. But
There's always a but.
right, this warm-up model had issues. The Klein-Gordon equation it produced was massless, which isn't always realistic, and more importantly, it didn't fully determine the metric G in empty space.
Ah, okay. So it couldn't describe the vacuum spacetime properly. How did the topological fields fix that?
That's where the richer structure comes in. By using that combination of 0, 1, and 2 forms, the framework naturally allows for mass terms to appear in the equations for the fields.
So you get massive particles, which is good.
Yes, and critically, the matter-induced metric G tilde, using the topological fields, becomes more sophisticated. It includes terms that depend not just on the fields themselves, but also directly on the curvature of spacetime, the Ricci scalar, the Ricci tensor.
Curvature terms built into the matter metric itself.
Exactly. And these terms involve fundamental constants related to the Planck length, the smallest possible scale. This allows the framework to determine the metric G even in a vacuum, addressing that key limitation of the simple scalar model.
Okay, that makes sense. The more complex matter description leads to a more complete gravitational theory. So let's look at the full picture again. The entropic, topological, and geometrical action.
Right. The action is still the quantum relative entropy between the background topological metric G tilde and the matter-induced one G tilde. An interesting technical point is that the entropy of G tilde itself is 0, which simplifies the math a bit.
And this full action, what does it give us in terms of physics we know?
Well, again, in the appropriate limit, weak coupling, low curvature, it reduces beautifully. You get back the Einstein-Hilbert action for gravity with zero cosmological constant in this specific limit, coupled to the scalar part of the topological matter.
So standard gravity coupled to a scalar field.
And you also recover the massive Klein-Gordon equation for that scalar field in curved spacetime. So it matches established physics in that regime, which is a crucial check. And it determines the vacuum structure.
That's quite compelling. Now back to this G field, the auxiliary one. You said it might be more than just a mathematical trick.
That's one of the really intriguing possibilities we're exploring. While it's introduced to help with the calculations, this G field, or G tilde, might actually represent some new physical degree of freedom.
A new field influencing gravity.
Potentially. When we use it to rewrite the original entropic action, we can split the result into two pieces. One looks like a modified Einstein-Hilbert action for gravity, let's call it LG, and the other is the action for the matter fields, LM.
Okay, separating gravity and matter?
But the gravitational part, LG, is dressed by this G field. And importantly, this LG naturally includes that emergent cosmological constant, lambda G, which depends only on the state of the G field.
So the G field itself could be the source of dark energy. Its value determines the universe's acceleration.
It's a very exciting prospect. If the G field is close to a simple state, like the identity matrix mathematically speaking, then lambda G is small and positive, which is consistent with what we observe cosmologically.
Wow. And the final equations, they involve this G field too.
Yes, the modified Einstein equations derived from this whole setup involve both the standard metric G, the G field, and the usual stress energy tensor from matter. But, as I mentioned, they remain second-order equations, which is theoretically appealing.
This definitely opens up a lot of directions. What are the next big steps for this line of research?
There are quite a few. One major avenue is quantization, trying to apply the rules of quantum mechanics to this whole framework, maybe using canonical quantization methods. That could give us profound insights into quantum gravity itself.
Tackling quantization head-on.
Absolutely. Another key area is understanding the G field better. Is it just dark energy? Could it potentially play a role related to dark matter as well? That needs investigation.
Two cosmic mysteries potentially linked to one field. That would be incredible.
It would be a huge unification, yes. We also need to see how other forces, like electromagnetism, fit into this picture. There are ways to include gauge fields, but that needs more work.
And presumably finding actual solutions to these new equations.
Yes, that's crucial. We need to find solutions, analyze their properties, see if they describe realistic scenarios, black holes, cosmological evolution, and so on, and ultimately compare predictions to observations. Does this modified gravity make predictions different from Einstein's theory that we could actually test?
Putting it to the experimental test, the ultimate decider.
Exactly. The fundamental takeaway, though, is this attempt to tie gravity directly to quantum operators, to information, to entropy. It offers a potential bridge between general relativity and quantum mechanics, which is something physicists have sought for decades.
A new perspective on unification.
We hope so. It might even provide tools for thinking about quantum gravity in what's called second quantization. And then there's the question of how this entropic action behaves at different energy scales, its renormalization group flow. That could connect it to particle physics phenomenology and maybe suggest other experimental signatures.
It's a vast landscape. Okay, let's try to sum up the key takeaways for everyone listening.
Sure. So the big idea is gravity as an emergent phenomenon, not fundamental. It arises somehow from entropy and the quantum information inherent in spacetime.
Driven by the difference between the actual space-time geometry and the geometry suggested by quantum matter fields.
Right. And these topological matter fields play a key role in making the theory consistent, allowing for mass and describing vacuum spacetime.
Then there's the introduction of this auxiliary G field, which helps derive modified gravity equations.
Equations that look like Einstein's but are dressed. And importantly, they naturally produce a small, positive cosmological constant linked to this G field itself,
which might connect to dark energy, maybe even dark matter. And the ultimate prize is this potential unification of gravity and quantum mechanics.
That's the hope. But It's really important to stress this is very much ongoing research. It's an active frontier. There are many open questions, lots of work still to do.
Absolutely. But it definitely gives you a different way to think about gravity, doesn't it? The force we feel constantly, maybe just a statistical outcome of deeper quantum information processes.
It's a profound shift in perspective, if correct.
For those of you listening, if this has sparked your interest, definitely look more into entropy, quantum entanglement, the holographic principle, and these ideas about emergent gravity. There's a lot out there.
Indeed. Keep asking questions.
Well, thank you for taking us through this fascinating and, let's be honest, pretty complex territory. We hope this deep dive has given everyone a glimpse into where theoretical physics might be heading. Thanks for joining us on the Science Corner.